Now we'll be discussing what we call the moments of random variables. All right, so in discussing that, we'll start with what we call mathematical expectation of random variables. And what we mean by that, it is simply the expected value. So when we talk about mathematical expectation, or simply called expected value, we mean the summation of this here. You need to know that x is the random variable. So given a random variable, x, all right, the mathematical expectation is what we have above. All right, so that's that. Now we, as we'll see very soon, what we call mathematical expectation is just a smaller part of what we call moments of random variable. Is just one part of it. So the mathematical expectation in essence actually is the mean over, so the long-term mean. All right, so we also write it this way. All right, I may put mu here, but the Greek alphabet called mu. So usually we may not write it the way it is above. We may just write this is equal to mu. So we usually don't write it together. So, but what we have above here above is still the same as what we have below. So what we have here is the same thing as this. So we are saying that when we look for the mathematical expectation of a random variable, it should be approximately equal to, or if we say in the long term, it should be what you get from the population. For instance, if you take the age of young boys, perhaps maybe the ages of young boys in a particular class are, let's say, 12, 10, and 11. We may stop here. Okay, let's add a few others. 13 and perhaps 10 and perhaps 9. Now, supposing that there are more than this, let's assume the age continues and maybe we have like 100, okay, in a class, let's say 20 of them, but we're only able to pick 1, 2, 3, 4, 5, 6 of them, and we try, but to make it easier, let's just assume that we only have 6 people in the class, but when I pick 3 out of them, so of 6 people in the class, I may compute an average. Any 3 of them can be picked. It doesn't have to be these ones. So it could also be these ones. It could be maybe this, and this. It could be any 3. But assuming that we pick the average here, we pick the sample. Our sample is just, okay, made up of these 3, 1, 2, 3, and we find the average. Whatever we get, we are saying that it should be close to what we are going to get for the entire population. So this is the entire population, whereas 1, 2, 3 consist or make up the sample. And now if we're looking for that of the sample, we usually refer to what we call X bar. X bar is written like this: summation of X over N. Now I want you to know that although we may write this way, there is a possibility of writing what we have as mu here in in a way that is similar to what we have above there. But this time around, it's going to be summation. Actually, it's xi because you're summing all of them. So I will take value from 1. So I will take value from 1 to capital N, and we'll be dividing by capital N. So capital N, right? Whereas I is going to take values, okay, will have its values from 1 go to small n. Okay, so everything here divided by n. Now, the difference between the two is that mu says, okay, I'm working on this everything. That's mu here, the population mean is working on everything. So that means that means that our capital N is equal to 6. It's taking 6 values. But here, our small letter n is equal to 3 because we're only taking 3 values in the sample. All right, so we are saying that if you find this and you find this, in the long run, what you calculate here should be very close. What you have here should be very close to what you have here. All right, so we believe that if you do it well, you take sufficient sample, you should actually get something. So your estimate is correct. All right, so continuing with what we are saying about the moments of random variables, and specifically coming to mathematical expectation, which is what we are doing at the moment, we actually have this to be somewhat close to what we have here, what we have in any of these two, just that we are only considering a sample in this case. So because I is supposed to be from 1 and then to your n. All right, in this case. Now, so what are we going to have? Looking at this, when each outcome of the experiment has a probability of 1 over n, then this will be equal to, not in all cases, well, in the case where the probability of each outcome is equal likely, then we can have this. So it means that if the probability is equal likely, probability of xi in all cases will be the same. And that will be 1 over n. And that will make this become what we have here, because when you put 1 over n here, then it will be the same thing as what we have here. Okay, now we may write it in full just to make it clearer. Summation xi or all over n. So an I takes value from 1 to n, just like we showed here. All right, so the same thing applies here. I takes value from 1 to n. But we will not be writing this in all cases. We are only using this to illustrate. Okay, I'm trying to illustrate what happens in reality. So you will be able to understand that what you have as your mathematical expectation is approximately equal to what you have here. Or somewhat very close. And it is believed that if you do it well, what you have here should be very close to this. So that's why it's called an expected value. You are expecting that it should be very close to this. And so that's why we write that the expected value of this should be equal to mu. All right. So, but in some cases, the probability may not be equal likely, so you may not put 1 over n there. But in the case of a fair die, for instance, tossed ones, the outcome are h and then you are going to, fair coin rather, you're going to have 1 over 2 as the probabilities. All right, so the probability of head 1 over 2, probability of tail 1 over 2, and for a fair die, tossed ones, the probability is going to be 1 over 6 for each outcome. And that's another thing you need to take note of. So we are saying that in this case, your probability of P of xi is going to be 1 over 6. But in the other case, it will be 1 over 2. So in this case, the case here, okay, probability of H, for instance. So, but if you remember, we may code, let's suppose we are interested in the number of tails that shows up. Head will be 1, head will be 0, and then t will be 1, and then so we may call this our x now, and so we may just refer to the fact that the probability of xi will be 1 over 2. So whether you have 0 head or 1 head, sorry, we're interested in the number of tails that show up. So whether you have 1 tail or you have 2 tails, it will be 1 over 2. So in the first case, this case, the probability of xi is 1 over 6, but in the second case it is 1 over 2. So you need to be mindful of the fact that in some other cases your probability of xi may not be constant. That is in cases where the elements are not equally likely to come up when you're doing your experiment, your random experiment. All right, so in that case, we may move on to see how the expectation works. Assuming that we have a fair die, tossed ones. Okay, so let's assume somebody casts the die now and says, okay, we want some numbers. The possible outcomes, as you may know, are 1, 2, 3, 4, 5, and 6. So we have our x, 1, we have 2, we have 3, we have 4, we have 5, and finally we have 6. Now, if we have this, the probability P of xi for all of them is 1 over 6. And so, since everything is 1 over 6, it follows the case we just discussed that Pi may change to 1 over n, or P of xi may change to 1 over n, but nonetheless, I would like to write the expected value as it should be written. That will help get used to it. Anyway, if you keep writing it, you get used to it. Now, this is it. And now, what would the mean be? Then it means that the mean will be multiplying each. Now don't forget that I takes value from 1 to n, and n in this case is 6. So I'll just put 6 here. Alright, so 1 multiplied by 1 over 6 plus 2 multiplied by 1 over 6. And you can go on and on until you get to the last one. Plus dot to save time, I won't be doing the others, but what we are doing essentially is saying 1 multiplied by 1 over 6, 2 multiplied by 1 over 6, 3 multiplied by 1 over 6, 4 multiplied by 1 over 6, 5 multiplied by 1 over 6, then 6 multiplied by 1 over 6. So I'll do the last one. That will be 6 multiplied by 1 over 6. And that's going to give us, we can factorize 1 over 6, seeing that everything looks, 1 over 6 is common to everything. So if we do that, we are now going to have plus 1, plus 2, 1 plus 2, plus 3, plus 4, plus 5, plus 6. And that will give us, this should give us 6, this should give us 10, this should give us 11, that should be 21. So 1 over 6 multiplied by 21. Alright, so having that, it becomes 21. If you divide, you should have 3 into 21, 2, 3 into, 3 into 6, that should be 2, and 3 into 21, that should be 7. Okay, so our answer will be 3.5 if you prefer the decimal, but if you prefer the fraction, it should be what you have above. All right, so that's the mean here. Now, we could also find the mean for a variety of other experiments, but this is sufficient to show us what we're talking about. Nonetheless, we may do one more example. What about a situation where we have a fair die tossed, let's say, once, and we have it to be that the number of heads that show up 0, 1. So the number of heads that shows up when we have no head, we have it to be 0. When we have one head, that's what we're interested in this case. And then probability will be this, the probability of xi. Now, if this is the case, what will be the mean? The mean will be expected value of x, as we said before, and it will be, you are going to have summation xi. Notice again that x here is capital, but x here is small letter, x here is small letter. Okay, and then I takes value from 0 to 1. And so that will be 0 multiplied by 1 over 2 plus 1 multiplied by 1 over 2 as well. And in this case, our mean will be 1 over 2. So that will be 0 plus 1 over 2, which will also be 1 over 2. All right. This is a simple case. What about if we toss our coin 2 times, and if you know, we're checking for the number of heads. You're already aware of that. We may have head, we may have tail head or head tail, and then we may have tail. I'm writing tail head and I'm not writing head tail because in this case I'm not interested in just interested in the specific case where you have one head or you don't have one head or you have 2 heads. I'm not interested in whether you have the head first or the tail. Doesn't matter in this case. So you're going to have these are the outcomes actually. So this will be the x now. In this case we have 2 heads, so we call that what? We call that 2 heads. Here we have just 1 head, we call that 1, and here we have tail 0. So it doesn't matter the arrangement. What matters is that the probability of each outcome is actually with it, is in the right place. So the probability of this one, if you know, is 1 over 4. The probability of this, because there are 2, TT or HT. All right, so those are the 2 of them, TT or HT. So let me use HT. All right, so it makes 2 over 4. And then for the last one, it is 1 over 4. Now, because of that, our expected value now, the mean, is going to be the summation of xi, probability of xi. I takes value from 1 to 0 to 2. Sorry, from 0 to 2. All right, and so it's important to know that it will always start from, you always go from the lowest value to the highest value. Ideally, it should have been written, 0 should have come first in the table, 0, then you say 1, then 2, but in some cases it may not be that way. What is important is that you know the probability, the correct probability associated with each value. All right, so I is taking value from 0 to 2, and then we start from 0, so 0 multiplied by 1 over 4 plus 1 multiplied by 1 over 4 plus 2 multiplied by 1 over 4. Now, note something as we continue. 2 multiplied, all right, 1 multiplied by 2 over 4, please take note of that. This should have been 2 over 4. All right. Note something that as we continue, if I decided to separate these two, TH and HT, then I would have 1 over 4 for TH and 1 over 4 for HT. And in that case, I will need to say 1 multiplied by 1 over 4, like what we have here, now would have been split to 2, and we're going to have something like 1 multiplied by 1 over 4 plus 1 multiplied by 1 over 4. So the first one here, this one will be coming from TH. The second one, this one will be coming from HT. But I don't think it makes, for the sake of space and ease of calculation, I don't think that's necessary, so you can put them together. But if we had it to be separated, then it will mean that what we said before will be holding. That means PXI would have become PXI. Sorry, please. PXI would have become 1 over n, as we said before. So it will be 1 over 4 for all of them. But since we have combined these two to 1, that will not hold. All right, so you can take note of that in case that's what you want to do. But just be sure that what you are doing is correct. All right, in that case, we are going to have 0 plus 2 over 4 plus 2 over 4, and that's going to give us 1 over 2 plus 1 over 2. Well, if you like, we may put the 2 together, not reducing anything. 2 plus 2 over 4. And that is going to give us 4 over 4, which will give us 1. So, and that will be the case. All right, so I think this is sufficient for to show us how to find the mean using what we call the mathematical expectation. All right, so what do we do now? We want to see some properties of what we call the mathematical expectation. The expectation has some properties, and these properties are very important because they form the basics by which you operate with the mathematical expectation. So what are the properties? The first property, so properties of mathematical expectation. The first property is that the expectation of x plus a, the expectation of x plus a will be equal to the expectation of x, x should be capital letter, plus a itself, where a is a constant. All right. Now, Please note that that applies to other places where you'll be finding, where you'll be seeing A. So let me put that as a general stuff. Where A is constant, the expected value of x plus A will give us what we have there. Number two, the expected value of AX will become A multiplied by the expected value of X. Number three, the expected value of X plus Y, where Y, okay, so we may write where A is a constant and Y, and X and Y are variables. So in that case, in such a case, then we're going to have what we are having here. Then it will be the expected value of X plus Y will be the expected value of X separately and adding that to the expected value of Y separately. And finally, the expected value of X multiplied by Y will be the expected value of X multiplied by the expected value of Y. All right, so these are the properties that you must take note of. So far, we have considered mathematical expectation from the standpoint of a discrete random variable. So everything we've done since we started has been with summation. So when we said the expected value we were talking about it with respect to the discrete random variable. That's why we said the expected value of X equal to summation X, and we said P of X. And don't forget we added I here. We said I takes value from 1 to n. But when this is for the case where our random variable is discrete. But what about in a case where it is continuous? Then we are going to have something like this. If you remember, we integrate when we deal with so the range may differ, it may not be from minus infinity to infinity, but generally we write it this way. X, but this time around we may just consider X multiplied by f of X. And then we have with respect to, so we are integrating this with respect to X. So this is the case when it is continuous. All right, having said that, let's take an example and see what we are going to have for the continuous distribution. Now, supposing that we have a continuous distribution f of x where f of x equals to 1, x raised to the power of 4 divided by 64, and 0 is less than x is less than 4. Now, you should know by now that if this is a true true density, probability density function, then if you find the differential, the integral of this, you should get 1. So this, it should not be from infinity. It should be, because we have the range from 0 to 4, we don't need to put infinity, minus infinity to positive infinity. I'm not yet taking an example of finding the expectation for this, but I just want to show that this is a true PDF, true probability density function. We are going to have 1 over 64 outside, then you can integrate x raised to the power of 4. And when we do that, we are going to get x raised to the power of 4, x raised to the power of 5. Oh, sorry. My intention was to make this x raised to the power of 3. So let's have that to be 3. 3. And that's going to be 3. 3. Okay, so not 3. It will be 4. When we integrate, so I've taken 64, 1 over 64 outside. So I'm going to integrate x raised to the power of 3, and that should give me x raised to the power of 3. I'm going to integrate x raised to the power of 3, and that should give me x raised to the power of 4 divided by 4. And when we do that, we are going to have this. I can have my 4 outside and have 0 here. And in that case, I'm going to have 1 over 64 outside. And so 4 raised to the power of 4 divided by 4. When I substitute my 4 there, I'm going to have 0 also. So 0 raised to the power of 4 divided by 4. And when we do that, we'll have 1 over 64. 4 raised to the power of 4. 4 can cancel one of the 4, so it becomes 4 raised to the power of 3 minus 0. And in that case, we're going to have 1 over 64 multiplied by 4 raised to the power of 3. And 4 raised to the power of 3 will give us 64. And that means 64 will be dividing 64. So 1 over 64 multiplying 64 now, and then we get 1. So everything becomes 1. So and that's it. So this is a true probability density function. So we can now use this to find what we really want. What we really want is to find the mean. And in this case, we are going to be looking for we're looking for the expected value of x, which will be what we said before, but the only thing is that the range will be different this time around. We will have it from 0 to 4. Then we have x multiplied by f of x. Our f of x in this case will be x raised to the power of 3. So divided by 64 with respect to x. And that will become integral. So we can put 1 over 64 outside. Integral from 0 to 4 of x raised to the power, this is 0 please, x raised to the power of 4, because the x here will multiply the x raised to the power of 3 here with respect to x. And when we integrate this, we are going to have 1 over 64. And when this is integrated, we'll have x raised to the power of 5. So let's put it x raised to the power of 5. And we will have 4 here. So the limit 0 to 4. And that will be divided by 5. X raised to the power of 5 divided by 5. And that is going to become 1 over 64. 4 raised to the power of 5 divided by 5 minus 4 raised to the power of 0. Oh, sorry. Minus 0. 0 comes into where x is now. Raised to the power of 5 over 5. And that's going to give us 1 over 64. Now 64 itself is the same thing as 4 raised to the power of 3. So into 4 raised to the power of 5 divided by 5. Now, because of the advantage of the indices here, we can take away these ones, and so we just have 2 false left. So if you prefer to expand everything and then do a reduction, you are fine. Just need to know what you're doing. All right, so in that case, we are going to have, we are now going to have 16 over 5 as our mean. So the mean here is going to be 16 over 5. That's it. All right, that's the case here. I think it's sufficient to, this example is sufficient to prove it. You just need to know how to, or to illustrate the expectation for a continuous random variable. You just need to know how to integrate whatever probability density function you are given. Well, that's it. All right, now we need to consider what the expected value of a variable which is a function of a random variable would be. So we want to look at the expected value or the expectation of random variables, okay, of a random variable that is a function of another random variable. So suppose y is a function of x. So we have y as a random variable and x is another random variable. Now, but y is a function of x. Permit me to use, we may use anything here. You may use g, you may use h, just means that it's a function of x. Now, y is a function of, so if I have this now, don't forget that we have always been writing f of x, maybe something like x raised to the power of 2 over something like that, and then we'll put some range of value like that, like that, like that. All right, so this is the important thing. Now, it means that x here is a random variable, but here we are saying that y is now a function of that random variable that is this. So let me give an illustration. For instance, suppose that, okay, let's use what I just wrote here. Suppose this is the case, and then we say y itself is equal to 2x plus 3. Then in this case, it means that we can find the expected value of y, but I'll write it in general here, please. Expected value of y in such a case as this will be a function so expected value of y will be expected value of g of f of x. All right, this is not a difficult thing. It may, all right, so it may look cumbersome. It may look cumbersome, but it's not difficult. Now, we could express this as y equals to g, and please, this is capital Y, take note of that, please, of x. In place of f of x, we may just put capital X, and we could express this as the expected value of y is g, or rather expected value of the function that is the function of x now. All right. Now, in this case, there is one more thing that we may write, and in that case, we may write the sample space for S to be a function of the sample space of, the sample space of Y to be a function of the sample space of X. So this is also a possibility. We may consider this too. Now look at this case. What we have here is not difficult. So I said Y is a function of X. So it's a function of X, function of this random variable. So when we want to find the mean, what we are going to do is expected value of Y will now become the expected value of 2x plus 3. Now, it will be safe to return to our rule about mathematical expectation, the properties we had there. All right, so property 1 talks about this expected value of x plus a equals to the expected value of x plus a itself. All right, now looking at that, we are going to have that come through here, but there is also something that we need to look at. Rule 2 rather, tells us that the expected value of a multiplied by x will be a outside multiplied by the expected value of x. And when we put that here, we are going to have, when we use those two rules, we'll have 2 multiplied by the expected value of x and plus 3. And that is going to give us, but we don't know the expected value of x, so we need to look for it. So we call this equation 1. So in that case, the expected value of x will be the integral from 0 to 2 of f of x dx, and f of x itself, in this case, just some space, in this case will be, or is, x raised to the power of 2 over 2. So with respect to x, and that becomes 1 over 2 outside integral of x raised to the power of 3, and from 0 to 2 with respect to x, that becomes 1 over 2 x raised to the power of 3, x raised to the power of 4 over 4. We really didn't check, okay. We didn't really check if this is a true PDF. So looking at this in a way, this is not a true PDF. So but if we have 9 here and we have 3 here, by examining it, it should be a true PDF. So that if this is raised to the power of, this is integrated, x raised to the power of 2 is, x raised to the power of 2 is integrated, we'll have x raised to the power of 3 over 3, and so 3 raised to the power of 3 should give us 29. Yeah, this will be a true PDF. All right, now looking at this, everything should remain as before, but 9, instead of 1 over 2, we now have 1 over 9. Right, just to make things clearer, I'll go over it again. I'll go over it again. 2, 2, 3. So what we are doing now is that, because I've changed this denominator from 2 to 9, and I've changed the range from before it was 0 to 2, now it's 0 to 3. Our range will become 0 to 3, right, 0 to 3, and the denominator is 1 over 9. So 1 over 9 comes out, 1 over 9 comes out. Every other thing remains the same, except for this. I've not changed this. So instead of over 2 here as we had before, it's now over 9. And so everything is balanced that way. Now, in that case, we are going to have, so if you integrate x raised to the power of 3, you get x raised to the power of 4 over 4. Sorry. Okay, yeah, so we are dealing with the mean, so it's okay, it's fine. Now we come here, and then we'll have 9 times 4 will be, don't forget, our limit will remain. So we may have, okay, let's bring it out. 9 times 1 over 4. I'm bringing 1 over 4 out from what we had before, so it becomes x raised to the power of 4, limit from 3 to 0, and that will be equal to 1 over 36. 1 over 36. Then x raised to the power of 3. Okay, no, 3 raised to the power of 4. 3 goes to the place. Okay, 3, when x is 3 here. Then we'll put 0 there. We are going to have 0 raised to the power of 4. And that becomes 1 over 36 multiplying, we have 3 raised to the power of 4. And that should give us 81 times 81. But looking at this again, is there something, okay, we can, times 81. And so 3 is common between them. So 3 should, that becomes 81 over, make things easier, 81 over 36. If 3 should go into 81, we should have 27. And if 3 should go into 36, we should have 12. Okay, so that's going to be the case here. 27 can be divided by 3 again. And in that case, we are going to have 27 divided by 3. We will get 9. 3 itself divided by, 12 divided by 3, we get 4. And that is going to give us, okay, so we may leave that as in fraction form, but if you like to go to decimal, it will give us 2.25. But what we have here is just the expected value of x. We don't have the expected value of y yet. So the expected value of x is what we have looked for. Starting from what we started to do, so this is it, and then we got it here. But we are concerned about the expected value of y. And so from equation 1, I think I'll just copy equation 1 from here to serve as a reminder. So now, don't forget that this is what we were dealing with, but we now know, so we may call this equation 2. So put equation 2, okay, so the value of from equation 2 into 1. Okay, from equation 2 into 1. And so if we do that, we are going to have expected value of y equal to 2 multiplied by, I think I prefer to use 9 over 4, but somehow we have used 2.25 here. So assuming that we had said expected value of x, kind of like the fraction thing. So, but if you like, you may not bother, just use your, but it's always preferable to use your fraction. It helps you with the decimal place and the others. All right, so from here, this will be, that should be 4.5. I guess that should be it. All right, so 2 multiplied by 2.25. Yeah, so that should be 4.5. You add 3, and that should give you 7.5. All right, so it means we have our mean for y. And so that will be all for the mathematical expectation. Thank you.